Welcome! These videos were recorded while I taught econometrics over Zoom, but they were edited so that the student faces, the questions, and my answers to those questions do not appear. That explains why you may notice some unnatural transitions and why the videos are shorter than a normal lecture. But hopefully you enjoy them anyway. Bye now. Alright, so today we get into our sixth lecture of Econ 480, and we're going to talk about GMM and empirical likelihood. So, as a way of recapping again, so last class we talked about efficiency of two-stage least squares. We cover weak IV, and we also talk about late. And up until last class, we just focused like 100% on the linear model. Today, we're going to transition to two methods that definitely work in the linear model, but are way less popular in the context of linear models for different reasons. But we're going to talk about GMM, which stands for Generalized Method of Moments, and Empirical Likelihood, which is a close cousin by now. And then we're going to discuss their asymptotic properties, why you may want to pay attention to these methods, and what are the pros and cons in terms of where they land in the field distribution, mostly used in I/O, and less so, way less so, in fields like labor or public, things like that. But anyway, that's what we're gonna be doing. So GMM, we're gonna start with defining the notation. We're gonna be using exactly the same notation, and despite the fact that today the methods are gonna be more general, I'll be paying some specific attention to the linear model so that it help us contrast the tools that we're gonna cover today with things that we talked before. We're gonna be using y, x, z, and u, and these variables are gonna be the same as before. Y and u are gonna be scalars, x, k plus 1, vector of covariates, and z are gonna be some instruments that are gonna be dimension l plus 1. Conditions are gonna be sort of like same as before. We're gonna assume the instruments are exogenous in this sense. We're gonna assume the expected value of z x prime is finite, and that the rank of the x prime is k plus 1. And we're going to start thinking about the linear model. But again, I want to start this as a motivation to say, look, when we look at the linear model, we define u. Of course, you can just take this to the other side. And so u is y minus x beta. And the moment condition was this one, the one that comes from the exogeneity assumption, expected value of zu is 0. And beta, we learned it was the value of this parameter that would solve this system of equations, where this is z and this is u. And so we have expected value of observed variables and parameters equal to 0. And we also learned that whenever we have more instruments than exogenous variables, that this may be an overdetermined system of equation. And so today we're gonna focus in particular, okay, in the case where you definitely have more instruments than endogenous variables, and we're gonna call this, we know, the over-identified case, and we're gonna use the difference between L and K to be R. Okay, so R are gonna be the number of moment restrictions that are quote unquote extra. Okay. And typically, people call R the number of over-identifying restrictions. So if you have easy case, you have one endogenous variable, and say you have 3 instruments, you're going to have 2 over-identifying restrictions. Capturing the idea that if you have one, that would be enough for identification. Now you have more than one, and so the benefits have to come from somewhere else and not from an identification point of view. But anyway, that's the terminology that we're going to use for today. So the above we just described is a special case of a more general class of moment condition models. And in order to represent those, we're going to use this notation m. M is going to be a function of y, x, z, and beta. Notice that y, x, z are the variables that we get to observe from this model. U is not here, but the parameter is also an input of this function. And this function is going to be L plus 1 dimensional. And then we know that beta is k plus 1 dimensional, which shares the same dimension as x. And so the moment condition model is just going to be the expected value of this particular function being equal to 0. And that's what is called a moment condition model. In the linear model, we know that this m, which I saw, is just z times y minus x prime beta. And the expected value of that is 0. In general, could be used for any type of nonlinear models. And there are many examples where this happens, okay? In econometrics, this class of models are called moment condition models, and this sort of like the terminology that I'm going to use in this class just goes to stats. They're often referred to as estimating equations as well. So you're going to see these depending on the type of papers on the subject that you read. So when we restrict attention to this particular family, when we have the expected value of a function m of the data and the parameters equal to 0, then there are multiple ways or multiple estimators that you can think about. But today we're going to consider two that perhaps are the most popular in econometrics, which are GMM, as I said, and empirical likelihood. They both will belong eventually to perhaps a larger family of estimators, sometimes called, say, generalized empirical likelihood, which will include the so-called continuously updating GMM. We're not going to go there. We're just going to talk about GMM and empirical likelihood. And if you understand the mechanics and the intuition behind these two, then moving forward, if you just need to cover the other estimators for whatever reason, it's just going to hopefully be an easy transition. All right. So as before, we're going to use P, okay, to denote the distribution of the variables that we get to observe, which in this case are y, x, z. Again, understanding that y, x, z, u satisfy the restrictions that we set before. And then we're going to have a random sample or an IID sequence of random variables that have come from this distribution P. That's the information that we have. Then we're going to define, as always, a sample analog of this moment condition model that falls at the population level when you take expectations. And we're going to denote this sample analog by n bar n as a function of beta. And it's just going to be 1 over n, the sum from 1 to n of mi beta. And I'm defining mi beta as just the function evaluated at the ith observation for y, x, and z. Okay, so this is just a short. And since we're going to be using this mi thing a lot, is a lot shorter than just writing all this expression that we have here on the right. So we're going to compute the average of mi, which in the linear model, okay, here I'm saying is just 1 over n, the sum of z times y minus x beta. And then if you write it in matrix notation, it just takes this form, which is 1 over n, and then the matrix multiplication, z prime y minus x beta. So up until this step, the idea holds in general for any function m. From here on, we're just paying specific attention to the linear model, which, as I said, we're going to be doing today as we move along. The method of moments estimator of beta is defined as the parameter value that sets the m bar sample analog of this equal to 0. Okay. Now, in general, this is not possible whenever you have more instruments or more moments, now you should say, than parameters you want to estimate. And so in that case, you just numerically, it's not possible to set the sample average equal to 0. So the method of moments is a well-known estimation method that holds specifically for the case where k is equal to L. You have the same number of equations than parameters you're trying to estimate. But whenever you have more, this approach doesn't apply. So the generalized method of moments has this idea that you want to define an estimator as the value that will set this sample average close, in some sense, that we're going to describe in a minute, to zero, given some notions of distance. Okay? So again, we know that in the method of moments, we can set m bar to zero. Can no longer do that. But now we're going to try to see if we can take this average as close to zero as possible once we have a way to define what it means to be close or far. Okay? The GMM estimator then is going to work as follows. We're going to let lambda n be an L plus 1 times L plus 1 matrix such that lambda n converts the probability to lambda, which is the limit matrix. And then we're going to assume that this lambda is symmetric and positive definite. Okay? So that will make this criterion function, which is a quadratic form. Notice that it's n times the sample average is a vector prime, this matrix times the sample average. Again, so it's a quadratic form in m bar. And so q here, beta, is a non-negative measure of distance between this vector and the origin. Okay. So if we set this lambda n to the identity, then what we have is that this criterion function, qn beta, is just the Euclidean norm. It's just going to be n times the Euclidean norm of this vector. And, as I wrote here, scale by the sample size doesn't really matter when you're computing this or trying to, maximize this function later on and so on. But it matters for defining later on test statistics and asymptotic distributions. So what's the GMM estimator? The GMM estimator is defined as a value that minimizes this distance, as we said before. So beta hat is just going to be the argument that minimizes Q and B. And of course, if it happens to be the case that you have the same number of equations and unknowns, then this estimator is just the method of moments estimator. So you can then say that the method of moments estimator now becomes a special case of GMM, which should not be surprising given the naming conventions that we're using generalized method of moments. Questions about the setting? So let's look at the first order conditions to see if we learn something interesting here. So beta hat sets 0 equal to the derivative of qn beta hat n with respect to b. And then if you look at this, it's going to be 2 times n times the derivative of n bar beta hat n with respect to b prime lambda n times n bar n beta hat n. And so if you just look at this expression that I wrote here, you can see that what GMM at the end of the day is doing is taking a linear combination of m bar b to 0. So this, if you think about it, is very similar. Well, it's the same in a way to what we did with IB and two-stage least squares, where we learned that whenever we had more instruments, in that case, than endogenous variables, that what two-stage least squares was doing is essentially was taking a linear combination of the instruments. Well, now we have this a potentially nonlinear model, and then we know that the sample average of this function m cannot be set to 0. So what GMM is doing now that you look at the first order condition, it's just taking a particular linear combination of m bar and setting that equal to 0. And later on, after we talk about EL, we're going to go back and try to see if we can give some meaning to this particular linear combination. So we'll get back to this. But now in the linear case, this becomes 0 equals 2 times n. And then I'm going to be using this expression for n bar that we have over here times z prime x prime lambda n times z prime y x beta hat n. And so we can split this and obtain z prime x prime lambda n z prime y, and then z prime x prime lambda n z prime x beta hat n. And so we can write beta hat n as z prime x prime lambda n z prime x inverse z prime x prime lambda n z prime y. Where I'm going to say the inverse here holds because we have, remember, the expected value of zx prime is, well, because expected value of zx prime is invertible, and because this lambda and the limit is positive definite, so we have a product of matrices that are full rank and therefore invertible. We used this trick multiple times before. We can also write, if we don't like this matrix notation, which we often don't, we can write it as a sum. I'm going to just write it up quickly. And then what we get from this slide is that two things. First is the interpretation of the moment condition, or the first order condition, sorry, as taking a linear combination of n bar to 0. And then we learn also that in the particular case of a linear model, GMM actually has a closed form solution. And this is a closed form solution. Beta. Whoops, I don't want to do that. Well, beta hat has a closed form solution. In general, in nonlinear models, this is not the case. Okay, so I said before, GMM often used in IO. In those cases, models tend to be nonlinear, and so you have to solve this numerically. Okay, you will have to define this quadratic form, and then use some numerical optimization to find the value of beta hat. Okay, but in the case of the linear model, it is not necessary to do any um, nonlinear optimization because there's a closed form solution given by this expression that we have over here. And even though it looks long, at the end of the day, it looks very similar to other expressions that we've seen before. For example, about two-stage least squares. All right. Questions. So, GMN has the usual two asymptotic properties that we often want from an estimator, one being consistency and the other one asymptotic normality. So we're going to prove this. I'm going to say today I'm going to use this notation. I'm going to let sigma be this matrix expected value of z x prime, which is finite. Okay. And then I'm going to say 1 by the weak law of large numbers. Okay, you have 1 over n z prime x, which is 1 over n the sum from 1 to n of zi xi prime, converses in probability to this sigma. Then 2 we're going to have by weak law of large numbers, 1 over n z prime y. It's going to be 1 over n sum from 1 to n zi xi prime beta plus 1 over n sum zi ui, conversion probability to sigma beta. And then remember that we know that lambda n conversion probability to lambda, and lambda is positive definite. So by, again, continuous mapping theorem, we have that beta hat converges in probability to omega sigma prime lambda sigma inverse sigma prime lambda sigma beta, which is beta. And GMM is consistent under these assumptions that we're using. Then we have asymptotic normality. And then in order to work with asymptotic normality, the first step is always to rewrite beta hat so that we obtain square root n beta hat minus beta. We always do that. That's convenient. It just looks like this. Exactly the same thing, except that you have u here instead of y. Sorry. You have here u instead of y, and then you have 1 over square root n because you have the square root n on this side. We're going to use the same notation as before. Sigma is going to be this expectation. We're going to introduce omega as the expected value of zz prime u squared, which in turn we're going to assume that it is well-defined, finite, and it is invertible. So then we have a couple of pieces as usual. The first one is, again, by weak law of large numbers. We have the same that we used before, which is sum from 1 to n of zi xi prime, converges in probability to sigma. Then we have that by the central limit theorem, 1 over square root n, the sum of zi ui, we're summing always from 1 to n, converges in distribution to a normal, which means 0, and variance omega. because expected value of z times u is 0. And we're just set here that the variance of zu is omega. Then by continuous mapping theorem, we have that square root n beta hat n minus beta converges in distribution to a normal with mean 0 and variance b, where b takes a sandwich form, as it usually does, and it's going to be sigma prime lambda sigma inverse sigma prime lambda omega lambda sigma sigma prime lambda sigma inverse. And now you can see why we decided to use some shortcuts for some of these expectations, because the expressions start getting long again, but it takes the usual sandwich form. Here we have the bread, here we have the meat, and here's the bread again. Okay. So when you look at this limit expression, b here, I'm just rewriting what we had in the previous slide. Then you realize that the asymptotic variance of GMM depends on this matrix lambda that we said at the beginning, any lambda will work. But then once you get to this point, you may ask yourself, okay, what would be the best choice for lambda? And you can define best choice as the value of lambda that minimizes this asymptotic variance. And so you can define that and say, well, we're going to say the optimal weighting matrix or weight matrix, we're going to denote it by lambda star, is the one that minimizes this asymptotic variance. That is, that gives us the GMM estimator with the minimum variance. And it turns out, I'm not going to show this, it's not complicated, but it requires some steps that are similar to others that we have done already. Turns out that lambda star is just omega inverse. So the best weighting matrix is just the inverse of the variance of ZU. And this yields what is known as the efficient GMM estimator, which just looks like this. So it's just the same expression that we had before, but whenever you see lambda, now you're going to have omega inverse. So omega inverse shows up here, shows up here. And then in the nonlinear case, you just define Q using omega inverse and you optimize that. In the linear case, it takes this closed form. And then when you plug in omega inverse here, you can see that a lot of things cancel out. And so the efficient GMM estimator has an asymptotic variance that is reduced, okay, or simpler. And it's just sigma prime, omega inverse, sigma, all this inverse. And that's the asymptotic variance of the efficient GMM estimator. Of course, in reality, we don't know sigma. Sigma, if you recall, is not sigma, sorry, omega is the variance of ZU. Or in other words, we wrote it as expected value of Z prime U square. And so then in reality, we never know this. But the idea is that omega can be estimated consistently. So whenever we can find some estimator omega hat and that converges in probability to omega, then this will work. And the only assumption that we need for that to happen is that this is positive definite, which is an assumption that we've been using before. I mean, it's symmetric by construction, but we need it to be positive definite to fall into this family of estimators that we define. And, later in class, we're going to describe estimators with these properties, although, we can guess immediately what it would be. And then once you estimate omega hat, then you're going to have the efficient GMM estimator by this expression over here, where you will replace omega with the estimator that you have. An important consideration is that here efficient, in the way that I describe it, means that this estimator has the smallest asymptotic variance in the class of GMM estimator with a set of moment conditions. And this is, in the same way that I said before, a weak concept of optimality. I mean, it's a lot stronger than, for example, when we talked about efficiency of two-stage least squares, because at least here we're not imposing extra assumptions, like, for example, homoscedasticity that we had to use to claim optimality of two-stage least squares. But it's still weak because you're not saying that this is the best thing you can do. You're saying if you restrict yourself to the family of GMM estimators where you're just using these quadratic forms, and that's what you are going to consider, then among that class, then the best thing you can do is this efficient GMM estimator. So as a notion of optimality is a weak one. However, there's this 87 paper by Gary Chamberlain that shows that actually GMM, this efficient GMM estimator, is indeed semi-parametrically efficient. And that means that, this asymptotic variance is the best you can do if the only information you have is that the expected value of this function m is equal to 0. Okay? And semi-parametric efficiency is certainly beyond the scope of this class. Conceptually, you can imagine that you can consider imagine you consider a parametric model that satisfies our assumption. That's typically referred to as a parametric submodel. And so you ask yourself, what's the best you can do in this parametric framework? Well, you know that you have things like the Cramer-Rao lower bound and things like that. And then you consider a different parametric model and a different one. And then eventually you consider all possible parametric models that will have the conditions that you need. And then you consider what's the worst that you can do among all those parametric models. And that will give you a bound. And what is shown is that GMM essentially achieves that bound. And that's the best that you can do. So that's strong notions of optimality, because it says GMM, okay, is a semi-parametric estimator that gives you the best possible asymptotic variance among all semi-parametric estimators, okay? So how do we estimate this optimal weighting matrix? Well, as I said before, given any weight matrix, okay, the GMM estimator is consistent, just inefficient, okay? So one example, if you just set the identity matrix that we talked before, well, that's easy. I don't need to estimate anything. Just plug in the identity matrix. We can get an inefficient GMM estimator. In the linear model, we have a better choice, which is we can use the Z prime Z inverse, assuming, that this is positive definite. And if you just plug this in, if you use this particular choice of weight matrix, okay, then just by replacing lambda n with this everywhere, you see immediately that GMM becomes the two-stage least squares estimator, which is something that we mentioned before. Two-stage least squares is a particular case of GMM. So the way typically you estimate the efficient GMM estimator is in 2 steps. And that's why sometimes this estimator is called a two-step GMM estimator. In the first step, you get a consistent preliminary estimator of beta, okay? And is in the context of the linear model, it is common that people just start with the two-stage least squares estimator. And if the model is nonlinear, it's also common that people will just start with the identity matrix. And that will give you a preliminary estimator of beta hat. You can use that, okay, to form residuals and then estimate the optimal weighting matrix, okay? Remember, this omega hat n, for example, you could use something like 1 over n sum, okay, in the linear model of zi prime u hat square, something like that. In the context of nonlinear model, it's just going to look like the same, but with the moments. And then once you have an estimator of omega hat or lambda star, then you're gonna implement the second step where you're gonna compute the efficient GMM estimator using your estimated weighting matrix. So it looks like this. In the general case, okay, let's say the beta hat is your first step estimator that you obtain by, say, two-stage least squares or using the identity matrix. And in the linear case, you're going to just compute the residuals like this, y minus x prime beta hat. In the nonlinear case, your residuals will have a different form depending on your model. But then you're going to define m hats functions, which in the linear case are z times u hat. In the nonlinear case, it's going to be m of y, x, z, beta hat. And then you're going to define this m star, which is the recenter version, okay? So here what we did is we took our observation and we subtracted the sample average, okay? And by doing this, what we achieve is that this function m star that we're using has this property that in sample, the average of this m star is 0, which is sort of like an analog of the expected value of mi is equal to 0. So what we're trying to do is in the population, we have that this or have zero expectation. We're recentering so that in sample they have 0 sample average, and then use that to estimate this optimal weighting matrix, which is omega inverse. So it can be shown by using the same arguments that we're going to use in the second part of this class that this lambda n star converts in probability to omega inverse. And then GMM using this weighting matrix is asymptotically efficient. And that's why, as I said before, this is typically referred to as the efficient two-step GMM estimator. And then it's true that right now people just say, I'm using GMM. If somebody says, I'm estimating this by GMM, you should expect that people do mean the efficient GMM estimator or a two-step GMM estimator, but it's often the case that people don't clarify either the efficient part or the two-step part. They just say GMM. And then one last piece of comment here is that notice that the way we computed this was by recentering these functions as here. We just subtracted the sample mean out of each of these m hats I. Of course, you could have ignored that and just use the m hats to define this lambda. This is also consistent, and in particular under under the assumption that the model is correctly specified. This will be consistent because the mean is 0. So it works out. However, some theoretical reasons, finite sample performance, and behavior of tests that you can use under the alternative hypothesis suggest that it is always a better choice to use a center version like this. Also, for validity of resampling tools that we're going to discuss at later in the quarter, for example, like the bootstrap. Okay, and our own Joel Horowitz actually had an important paper that showed that doing this recentering was important for the validity of the bootstrap in GMM settings. Okay, great. Okay, to conclude this part, there's something called an over-identification test, or sometimes called J-test. And the idea is the following. You consider your test statistic as the value of the criterion function that you're optimizing at the estimated parameter beta hat, the GMM1, which is just m, the average at beta hat, our estimator lambda star n, and the average at beta hat. And then it turns out that if the model is correct, okay, if it is true that the expected value of m beta is equal to 0, then this function converges in distribution to a chi-square with L minus k degrees of freedom. And so this is typically known as a test of over-identifying restriction. Remember that L minus k, we said R was the number of over-identifying restrictions. So the more over-identifying restrictions you have, the larger the degrees of freedom. And so in a way, what you're doing with this over-identification test is to see if these extra moments that you have, remember you have more moments than you actually need, whether this combination of moments actually seems to be valid or not. And so you have also, this is the behavior under the null. Under the alternative, you can show that this criterion function converges to infinity if some of these moments are invalid. Okay. And so the over-identification test rejects the null hypothesis. Okay, there exists beta such that the model holds, which is this, when our test statistic exceeds the quantile, which is just the 1 minus alpha quantile of the chi-square with L minus 1, L minus k degrees of freedom. So how is this used? Well, just typically people will report the value of the over-identification test at the end of their tables where they're doing things. Again, this is not typically used as a way to choose moments because, for example, you have 10 moments and you have 2 parameters, and so you reject, you know that there's something that is not fitting well here, but you don't know which moments are the ones that could be wrong or not. Having said that, there's a literature on choosing moments that also have issues or less used in practice, at least broadly. But this over-identification test is something you're going to see sometimes, often, I'll say, whenever GMM is used. And then people just report the p-value of these tests at the end of their tables just to get, say, some reassurance that the numbers are things that you want to perhaps believe, or if the p-value is very small, you may be careful about the interpretation that you're getting out of your estimates. But this is what the test does. It's essentially testing, sometimes called an omnibus test, where you test everything into one null hypothesis. Questions? So now we're going to continue the class today, and we're going to move to another approach that is called empirical likelihood. Empirical likelihood, I wrote here, is a data-driven, non-parametric method of estimation and inference for moment restriction models. This does not require weight matrix estimation like GMM, and is invariant to non-singular transformations of the moment condition. It was developed by Art Owen, who is a statistician at Stanford. Okay. I wrote, it is basically a non-parametric analog of maximum likelihood for this model. So, in just at the risk of being confusing, we're using non-parametric here, but we're using this restriction. So, of course, the combination of the two in our case is going to lead to a semi-parametric estimator. Okay. But here, conceptually, the idea is that you want to consider the moment condition. You want to do something like maximum likelihood, but you don't know the distribution because you're not making parametric assumptions. So you're going to do something else. And so empirical likelihood, or EL, may be viewed as parametric inference in moment condition models using a data-determined parametric family of distributions. The parametric family is going to be a multinomial distribution on the observed values. So what you're going to do is that for each observation that you have, you're going to have endpoints. You're going to define a parameter, P1, P2, P3, ... Pn, okay? And then that's going to be your parametric family of distributions, and then you're going to do maximum likelihood with that. Now, that thing that I just said, it makes empirical likelihood very different than parametric likelihood, because this parametric family will have n-1 parameters. So when you think about what I'm suggesting, we're going to have, it's n-1 because, of course, the probabilities have to add up to 1. Okay, so you lose 1. Otherwise, it would be n. But suppose you have n-1 plus the parameters that you want to estimate, which are like, say, k. Beta was the mentioned k. So you have, n-1 plus k parameters to estimate with n observations. And so when you say it like that, it looks like, well, that's not going to work out. But it turns out that it does. So let's see how. So I'm going to denote, as I said before, this multinomial distribution with this letter pi. It's just going to be the probability that you observe the observation I. And then this distribution is going to satisfy the moment condition if and only if, when you take expectation with respect to this distribution, you have the moment holds. And so in our case, the expectation is just the sum of pi times mi beta. This has to be equal to 0. If this is the case, then you have a parametric family of distribution that satisfies the moment conditions that in our model, which is that the expected value of this function m is equal to 0. The EL estimator is just going to be the value of beta that is going to maximize the multinomial log likelihood subject to some restrictions. And so, in particular, we're going to call the empirical likelihood function. I'm going to use this script R to denote the empirical likelihood function. Is just going to be a likelihood, which is the product of all the probability, joint probability of observing your data. Just since the data's ID is P1 times P2 times P3. That's the joint distribution that you observe what you observe. You're going to compute the maximum, okay, of the likelihood subject to 3 restrictions. The things that you observe happen, so you want the probability of observing an observation to be strictly positive has to be a probability, so they need to sum up to 1. I need to satisfy the moment condition, so it has to be that when you take expectations of this function m is 0. That's the restriction. And so mechanically, we're going to write down this likelihood problem as a Lagrangian problem. So you just take the log likelihood, okay? And then you have the sum of the log likelihood, which is this product here after you took the logs. And then you have the first restriction and the second one. The first one is implicit here when we took the logs. It's, when we don't have log of zeros well defined. So here in this notation, kappa and lambda are Lagrange multipliers. So, and as I said before, remember, we have n observations, and look at this. We are having the parameters that we care about, say dimension k, say k plus 1 or whatever it is. And then we have n here, and then we have, here kappa, which is dimension 1, and L, which is going to have the same dimension of the function m. So it's just going to be, say, L plus 1. So we have a lot of parameters. And in particular, we have more than data points. So there has to be a trick. To see the trick, we're just going to look at this Lagrangian problem, and we're going to compute first order conditions. So let's just work on that. Let's look at the first order conditions. We need a couple of derivatives here. First, we're going to take the derivative of this Lagrangian with respect to pi. So that's going to be 1 over pi minus kappa minus n lambda prime mi b equal to 0. Then I'm going to take the derivative with respect to kappa, and that's giving us just the sum 1 to n pi minus 1 equal to 0. And then I'm going to have the derivative with respect to lambda, which gives us just the sum from 1 to n pi mib equal to 0. So that's that. I'm going to take the first equation here. I'm going to multiply by pi and sum. So what we're going to get then is sum from 1 to n of multiplying by pi. So it's 1 minus kappa pi minus n lambda prime pi MIB, and this is equal to 0. And then this gives us that kappa equals n by using, I'm going to say 2 and 3. This is 2, this is 3. So now I'm going to take this equation again. I'm going to use that kappa is equal to n. And we're going to solve for pi. So if you solve for pi, then you're going to have this as 1 over n times 1 over 1 plus lambda prime MIB. And we here see the first element of, if you want to say, the magic behind empirical likelihood is we said we had n parameters, which is all these probabilities. But it turns out that these parameters, they have a closed form, and they only depend on I through the data. Other than that, they just depend on this Lagrange multiplier lambda and b, which is the parameter that we're going to be estimated at the end of the day. So then, if you write it lambda, I'm going to say here using this, in turn, lambda b solves let me call this g of lambda sum from 1 to n, let's say 1 over n here, MIB 1 plus lambda prime b. Solves g lambda equal to 0. So we have two equations. If we write pi only as a function of b, it's just going to be 1 over n times 1 over 1 plus lambda b prime MIB, and lambda b solves g lambda equal to 0. And this is what we learned from these first order conditions. We can write each of the yield probabilities as a function of b only. And I know lambda shows up here, but we're just solving lambda, or choosing lambda as the value that solves g equal to 0, which g is this expression over here. Okay, so from the first order conditions of empirical likelihood, we have a closed form solution for each of the pi's, and we have a representation for the Lagrange multiplier lambda, both as a function of b. We haven't estimated b yet, so this is for a given b. For a given b, you can have expressions of kappa, p, and lambda. And so now this simplifies the problem because we had a lot of parameters going on, and now all of these actually are functions of b. Okay, kappa is actually simpler; it's just a sample size. But then lambda is a function of b, and p is a function of b. And so now everything becomes a function of the parameters that we care about. So how do we go from here? Well, we'll just go back, and now you look at the log likelihood function that we had before, okay? And then you can write it like this. This is what it was the sum of the log of n times pi. But now we have an expression for pi, that depends only on B. And so you can say the log of what I call later R and B, which was the likelihood. Whoops. Just gonna be the negative of the sum of the log of 1 plus lambda B prime mi B. And I'm going to call beta tilde, and the EL estimator is the R max of the log of RB. And that's the empirical likelihood estimator. So, two comments here important. First, okay, empirical likelihood optimizes this criterion function. Okay, so this first optimization problem that we did over all the PIs, whatever, in practice you don't do it because you do it once, you realize that the criterion function you're optimizing is this one, okay, and then you just work with this criterion function. That's the first part. The second part, notice that this is all nice, but then this lambda b that is over here is actually solving another equation. So it's not just an isolated lambda b. Lambda b is defined by solving that equation. So we can rewrite this as the function of, instead of b and b alone, as a function of b and lambda. So let me write Qn, which is going to be our objective function, and now viewed as a function of b and lambda separately. And then I'm just going to put lambda here. Now lambda is just a parameter here. Well, it turns out that if you just take this criterion function now as a function of lambda and b, and now take first order conditions, what you have is that the derivative of this guy with respect to lambda is going to be a negative, say sum from 1 to n. Forgot to write the 1 to n everywhere. Of mi b 1 minus lambda prime mi. Let me rewrite this. Sorry. I'm going to write because I want to be clean. Take first order conditions. So I'm going to say beta tilde n, lambda tilde n, jointly solve the following. So we have derivative Qn at beta tilde n, lambda tilde n, with respect to lambda is negative sum from 1 to n mi beta tilde n plus 1 plus lambda tilde n prime mi beta tilde n equal to 0. And the derivative of Qn with respect to, if you want, b, just going to be sum from 1 to n. Okay. The derivative of mi beta tilde n prime derivative b prime times lambda tilde n 1 plus lambda tilde n prime mi beta tilde n equal to 0. And so another way to describe empirical likelihood estimator is that beta and lambda jointly solve this problem and these first order conditions. Okay. So now thinking about how do you implement this in practice? Well, now you see it's not difficult, at least conceptually. First, you define your criterion function as a function of lambda and b. Lambda is the Lagrange multiplier. It's negative the sum of the log of 1 plus lambda, your moment function at b. And then you need to maximize with respect to beta, minimize with respect to lambda, which lead to two first order conditions. One with respect to lambda, which is this. Notice this equation over here is exactly the same of what we said lambda solves g equal to 0 before. Yes, there's a 1 over n here, but that's irrelevant. Okay. Before we said lambda sets g equal to 0. Well, that's the same as saying lambda satisfies the first order condition of this problem. That's exactly g. And then when you take the derivative with respect to beta, you have a moment that just has the derivative of the moment functions times lambda divided by the same thing. And these first order conditions we're going to sort of like use in a second, but that's how you implement empirical likelihood. One thing is important. Notice that here we just wrote this for any moment function m. It doesn't matter if the model that you have is linear, okay? EL doesn't have a closed form solution. As opposed to GMM, where we said in the linear model, it actually accepts or admits closed form representation for beta. In the case of empirical likelihood always has to be solved numerically, always requires numerical optimization, never has a closed form solution, even if the model is linear, okay? And so from a computational standpoint, in particular, if you're dealing with linear models, then empirical likelihood has from the get-go a clear disadvantage, which is, computationally is more complicated. Then oftentimes you'll hear people say that empirical likelihood is computationally difficult or more difficult at least than GMM. Now, to be clear, the reason is not because you're solving a problem like this with many parameters, because you never do this in practice. In practice, you just define this criterion function and optimize with respect to beta and lambda. But these outer and inner products that are sometimes called when you just estimate with one and the other one and so on is more difficult than estimating typically the GMM criterion function that only depends on beta, and it doesn't have a parameter like lambda over here, right? Remember that the dimension of lambda is equal to the number of moments that you have. So if this beta here is k plus 1, lambda was going to be L plus 1. So you're adding sometimes a fair number of parameters to the optimization problem. But mechanically, this is what it takes. And there are packages in R, Python, MATLAB, and so on to implement empirical likelihood. As far as I know, there's nothing like that in Stata that mostly focuses in type of linear models and less so on nonlinear models. Questions about how we define the empirical likelihood estimator. All right. So what are the asymptotic properties? The asymptotic properties of EL are actually clean. I wrote here, it turns out that the limit distribution of the EL estimator is the same as that of the efficient GMM. So when you just look square root n beta tilde minus beta, converging distribution to a normal, it means 0, and look at this. This is the limit invariance of the efficient GMM estimator. So conclusion, empirical likelihood is semi-parametrically efficient in the same way as GMM is semi-parametrically efficient. And so we're not going to prove all this. It takes some additional step relative to GMM. But what's most interesting is to compare the first order conditions, okay, of empirical likelihood and the two-step GMM estimator, because then you realize that in reality, what these two are doing are taking more or less the same linear combination of the moments, okay, that we were discussing before, but we're using different estimators of these weights, quote unquote. So instead of proving something like this, you're going to believe me that EL is consistent and asymptotically normal and semi-parametrically efficient. So at this point, we have that both GMM and empirical likelihood have exactly the same asymptotic properties, and that the one caveat is that empirical likelihood appears to be computationally more intense than GMM. We're going to look at the first order conditions to see if we can hint some differences between these two that are relevant for applied work or for theory. So to do this, let me rewrite the first order condition of the EL estimator. This is just, I want to make the EL first order condition, which remember, we just characterize as these equations over here, but I want to make it look more like the type of GMM first order condition. So I'm going to use some notation over here. Remember, M is the moment function, which in the linear model is this, okay? I'm not going to be doing the linear model too much, but I'm just going to make the connection. Capital M here is just going to be the derivative of the moment with respect to beta, okay? In the linear model, actually, it doesn't depend on beta. It's just Zx prime, and we see that appear everywhere. And then the expected value of this derivative, we're going to call sigma. Well, in the linear model, that was the expected value of Zx prime, okay, which is an object that we've been using all the time, which again, in the linear model, doesn't even depend on beta. But in general, it may depend on beta, so I'm going to make the dependence explicit. Then omega is the expected value of M prime, or the variance of the moments, which in the linear model was just expected value of Z prime U square. So I'm going to be using this notation. The two elements that I really need are sigma, which are the expected value of this derivative, and omega, which are the variance of this moment. And, if you have some memory that takes you back to the stuff that you learned in 480-2, then you will see that these objects are similar to those that you play around for an entire quarter. So the EL estimator we wrote before are such that beta tilde and lambda tilde jointly solve these two equations over here. And I'm going to manipulate them so that I get a clean expression. So I'm going to use that 1 over 1 plus a is equal to 1 minus a over 1 plus a. Okay? This is just algebra. Simple. So I'm going to say, note that all these expressions contain 1 over 1 plus lambda prime mi, and this is our a. So I'm going to be using these expressions over here with this trick. And so I'm going to take this guy over here. I'm going to say this is equal to 1 over n, sum from 1 to n, mi beta tilde n, minus 1 over n, sum from 1 to n, mi beta tilde n, mi beta tilde n prime, lambda tilde n, divided by 1 plus lambda tilde n, mi beta tilde n. And this is equal to 0. So I just use this trick, okay, that I'm defining. So we can now solve for beta. Sorry, for lambda. Solve for lambda tilde n. And what we have is that lambda tilde n equals 1 over n, sum from 1 to n of mi beta tilde n, mi beta tilde n prime, 1 plus lambda tilde n prime, mi beta tilde inverse. So here all I did is I moved this to the other side, and then I took this term inverse back, times m bar n beta tilde n, which is this guy over here, right? This is m bar at beta tilde n. So that's that. And so I'm now going to use this in the other equation. And then we get this 1 over n, sum from 1 to m, of capital Mi beta tilde 1 plus lambda tilde n prime Mi beta tilde n this times lambda, but lambda is this expression, so I'm going to replace. I'm going to put back all these objects. And now when you look at this, and I know it's kind of like a pain to do, but now you see that EL also sets a linear combination of m bar n to 0, exactly as GMM. Okay, it requires some additional manipulation, but that's it. And what is this? Well, it turns out that if you just look at this object, we're going to call this sigma tilde n beta n. This is an estimator of this matrix sigma. And then I'm going to call this omega tilde n of beta n inverse, which is an estimator of this matrix omega that we had before. Then instead of using the usual 1 over n as a weight, they use the empirical likelihood probabilities. Okay, they use these PIs that we defined before, which is 1 over n times 1 over 1 lambda prime mi. That's what they're doing. They're estimating these derivatives and this omega function using the EL probabilities. And so when you look at the first order condition, you know that this is exactly what we found. And when you just take and compare to the GMM one, well, GMM had essentially sigma hat n beta hat n prime. It had omega hat star whatever inverse n, and it had m bar beta hat n equal to 0, where sigma hat and beta hat n was 1 over n, the sum from 1 to n of this mi evaluated at the GMM estimator, and omega hat star was based on a preliminary estimator. So there are two differences. The first one, EL uses EL probabilities. Oops. to estimate sigma and omega. GMM just uses 1 over n. And the second one, GMM, uses a preliminary estimator to estimate omega, whereas EL estimates all in one step. So omega tilde n is a function, indeed, of the EL estimator. If you look at the first order condition, the EL estimator is here, here, and here. Whereas in GMM, it doesn't really show up in the middle because it uses a preliminary estimator. Other than this, the first order conditions are exactly the same, and they are both using a linear combination that is based on sigma prime omega inverse. That's the linear combination they're taking. They're just estimating the linear combination differently. That's why they're both asymptotically efficient. Now, a topic that is way beyond the scope of this course is something called second order asymptotic properties. As you remember, when you do first order asymptotic properties, at the end of the day, you're essentially taking a Taylor expansion and keeping the main term, killing all the other ones. But in principle, you could imagine that you take, more terms in the Taylor expansion, for example, the first two, and then you kill the other ones. And then it turns out that when you take more terms in the Taylor expansions, when you study the properties of these estimators, EL starts having better properties by using better estimators of these terms, sigma and omega. And better means that these EL probabilities have advantages over the 1 over n that GMM uses. And by not using a preliminary estimator, that gives better properties to empirical likelihood. So when I say that both empirical likelihood and GMM are both semi-parametrically efficient, that's correct. They both are. But if you just start digging deeper about the differences between these two, then there are a number of papers that show that empirical likelihood has better asymptotic properties and may perform better. Of course, that comes at a cost, which is usually EL is computationally more difficult than GMM. So to conclude, if you compare the first order conditions of GMM here and empirical likelihood here, you can see that they look sort of like exactly the same. Okay, and here I just listed the difference that I said before. I'm going to go over them one more time. GMM uses omega hat as a consistent estimator of omega based on a preliminary estimator of beta. So not surprisingly, these two estimators uses sort of like the same linear combination. They're equivalent. Okay. Using a different estimator of the Jacobian matrix sigma and the absence of a preliminary estimator for omega gives EL some favorable second order asymptotic properties, which are the stuff that we're not going to cover in this class, but it's good that at least you're aware that this happened. And then the cost that you have an empirical likelihood is computational complexity. And these are topics that sometimes, some years, I cover in Econ 481. So that's it for today. Questions?